at 4, you shoot it, its head rolls off. It's going to float through the air in a more physically realistic way, okay? Without doing this, it's going to look kind of silly and like an animation, but using Havoc's techniques, it's going to look realistic. And when something explodes, things blow up in a very appealing way, okay? And it's appealing because, well, it's mimicking what happens in nature. It's actually solving the underlying dynamical system to make it look realistic. And that's kind of hard to do in real time. So that's why these guys are so good. They've got clever ways of doing it in real time, but doing it rapidly, so you can incorporate it into a video game or into an animation. Okay? Because it's no good doing this if it's going to take a day to run. You want your video game to be realistic, but also to be responsive and quick. Okay? So these guys are pretty good, and they've been doing this for a long time. They're pretty successful. Here's one of their more recent things I took from their website. They're working on this at the moment. They're pretty outspoken. You can go and click on this link here, and you can see what I think their CEO, something called Mark O'Mara, Mr. O'Mara anyway, has to say about his difficulties finding good quality graduates. And you can do this kind of stuff. He bemoans the fact that he finds very few people can actually come along and code up a Runga Kutta method and slot into a team like this to hire abroad in France, basically like that. So hopefully at the end of this course you'll be able to send an email to Mr. O'Mara and apply for a job. He'll give you a job, okay? We won't be giving out anymore. Okay, so let's look at another topic. Topic number 6, getting even more complicated. An ordinary differential equation is a puzzle where you have to find a function of one variable. The answer to the puzzle is a function y which depends on a single variable x, or maybe t, or whatever it might be. A partial differential equation is a similar beast. It's a puzzle involving some quantity, in this case, for example, phi, which is the potential. This is an electrostatic problem. You've got a charged conductor creating electric fields in space. You've got to work out the potentials. And you can solve that by solving an equation like this. The divergence of the gradient of phi is equal to minus the charge density over epsilon. Okay? And this is just shorthand for a bunch of what are called partial derivatives, d phi dx and d phi dy. So phi is an unknown function, and it varies in the x direction, it varies in the y direction. And we can measure how it varies in the x direction by taking d phi dx. We can measure how it varies in the direction by taking d phi dy. And these variations aren't just arbitrary. The laws of nature tell us that these variations, if you put them together, measure them in this particular way, so you look at these particular variations, they have to equal the charge density at that point. Okay? So you have a charge density, solve this equation, you're going to get the electric potential, that gives you electric field. Okay? So you've seen some of this stuff in second year electron mag, and you'll see more of it in third year electron mag for the DC students. Presumably the same with the Maynooth students. You've seen some of this already. Again, the details don't concern us too much as yet. I'm just trying to set the scene. Where is this stuff useful? Well, for example, you want to apply this stuff in real life. Here's Tom Cruise in a movie about 10 years ago, which seemed at the time very high-tech. Minority Report. They had one of these touchscreen things, which nobody had ever seen before. It looked like something from the planet altogether. Now everybody's got a touchscreen. They've got a touchscreen in their pocket. Okay, so it's amazing what can change in 10 years. But touchscreen technology is often built using what are called capacitive sensors. And I've got a student working at the moment with Cypress Technologies he's over in San Jose at the moment, of all places, working on designing capacitive sensors, which is where you have these little electrodes, and by pressing on them with your finger, by touching one with the finger, you change the capacitance of the device, and that can be measured. And once you can measure that change in capacitance, you can work out where that finger is. And once you work out where the finger is, you know where the person is touching. Okay, and that's how a touchscreen sensor, a touchscreen device works. It solves an electrostatic problem like this. Okay, but it doesn't solve them analytically. Again, you can only solve them using numerical methods. So these guys work with a package called COMSOL, which is a big finite element solver. Finite element method is a numerical method, and it uses that to solve this for complicated 3D geometry. So they can design these little sensors in the most efficient way, make them nice and neat, make them nice and small, make them very responsive, make them consume less energy, all those kind of things. Okay, so in doing that, they've got to solve problems like this. So again, if you want to get a job, you go and you study EE317, you learn how to do partial differential equations, you go and talk to COMSOL and they give you a job working on the finite element method, and you go and design stuff for Tom Cruise, okay, and make a million euros. So it's all very easy. Pay attention to this course and you're going to get 10 jobs at the end of it, okay? Last topic, you'll be glad to hear. Topic number 7, pseudo-random numbers. Okay, so we live in a very random world. The world is very random. Random things happen all the time, and that's kind of fun. We use that to our advantage the whole time. We humans like to play games. We like to play dice. We like to play cards. We like to bet on horses. We like to embrace uncertainty, okay? Engineers and physics, not so enamored with uncertainty and randomness. It makes life a little bit difficult because you have to somehow make devices and systems reliable in the face of randomness. So for example, our poor colleagues over in NUIM, some of them are randomly dropping out because of some random problems with our internet server. So they've been very good and they're logging back in. But that kind of randomness isn't very good. But nonetheless, as engineers, we have to understand it and deal with it. So here's an example here of one of my PhD students who was doing a project whereby he was trying to find ways of locating people indoors. Indoors, you can't use GPS because the GPS signal doesn't work indoors. It gets blocked by the walls. What you can do is you can use Wi-Fi. So he walks around a device like this and he can hear several Wi-Fi access points. And those access points act like satellites, okay? And by locating where he is relative to those access points, he can work out where he is. He can work out where he is in the building. Okay. He can work out where he is in the building by doing this. But the problem is, when you're walking around with your little iPhone or your laptop or whatever it is, and you're measuring your Wi-Fi signal. I need to take this, it's from the guy in the loop. Hi, Seamus. Can we get you back later on, Ash? I was just on a break. Phone calls. So the problem is you walk around, you get these Wi-Fi signals, and the problem is they're random, they change. Because someone gets in the way, or someone moves a door, or some people walk by and it changes the Wi-Fi signal. It's not as strong as it once was. Okay, so it's a random signal, it's not reliable. So for example, here he did a little experiment where he went to a location and set something listening there, and this is the spread of signals that he got. And it has a histogram, it has a statistical distribution. Okay, it isn't just a constant, it changes over time. So engineers and physicists need to be able to work with randomness. We need to be able to model it, we need to be able to understand it. Okay, that's just one example, there's millions of examples. No. So what's the problem? Well, the problem is the world is random. Random things happen. People make phone calls. Connections drop. Horses fall over at the last dance. And that's all random. We don't understand it as humans, and that's what makes life interesting and frustrating and annoying and fun. But when we're trying to understand randomness, we're trying to model it as engineers, what do? We use one of these things, computer. Okay? Now, the last thing a computer is random. Computers are not random. They're designed in clean rooms, very clean, high-tech environments to be absolutely deterministic and do exactly what we want. They're not random. Nothing is left to chance. So how can we make something random? How can we simulate or model a random process using a machine which has been engineered using billions of dollars of technology to be deterministic? There's a problem here. Okay? So what we do is we don't make, when we study randomness or we try and make a random process as an engineer, we don't make a random process, we get what's called a pseudo-random process. And what a pseudo-random process is, it's a process that to all intents and purposes looks random. Okay, it looks random, someone else. But it isn't actually random. All it's doing is stepping through a sequence of states in a predetermined fashion. And it's completely predetermined, nothing random at all. But the number of states it steps through is so large that any given step to a casual observer appears random. Okay, so here's an experiment I did in my computer earlier on. Went to iTunes, I asked iTunes to make a random playlist for me, and I came up with, whatever, 25 supposedly random songs. Okay? But this isn't random. iTunes and your iPhone or whatever MP3 player you have has an algorithm for making supposedly random, inverted commas, random selections of songs. They're not random. They just appear random to you. And this kicks off a whole can of worms because when the iPod came out first, there was a great deal of controversy because humans were effectively just monkeys. We're only down from the trees for a million years. We're very unsophisticated creatures, really. We have a very poor intuition for randomness, and we can get confused very, very, very easily. So there's a big controversy around the time of people giving out because they felt that their iPods and their MP3 players weren't random enough, because they would put on a random shuffle and lo and behold maybe two songs from the same artist would turn up side by side, or two songs from the same album would turn up side by side. And people gave out because if something was random, how could you possibly have two things from the same album turning up side by side? I've got 20,000 songs. How could you have two songs from the same album turning up one after the other? That couldn't be random. And of course it is random because that kind of structure appears all the time in everyday life. There's coincidences. You see people that you didn't expect to see. This structure appears. It would be very strange if you didn't have that kind of structure appearing randomly. Okay? But people, their intuition tells them that random means completely random and completely without order. And in actual fact, these little pockets of order appear. Okay? So this is one of the problems. You can read about it here in this web page. And people giving out about this, this seemingly unrandom. So what Apple had to go and do, they had to go and modify their algorithm to actually make it less random. Less strictly random, but more apparently random, if that makes sense. Just to keep people happy, okay? So they had to cheat and actually make it less random, but sufficiently random that humans wouldn't give out. Here's another thing about randomness. Very important that people understand probability and statistics. Here's the example I suggest you're going to have a read. It's a tragic story of a lady in the UK who was arrested on suspicion of killing her two children. The poor lady was a tragedy. Her two children died, sudden infant death syndrome, and she was arrested and served time because it was alleged at her trial that the probability, statistically, the probability of two children dying of this terrible sudden infant death syndrome was so small, the number of 1 in 73 million was mentioned, that it could not have been a random chance occurrence, and therefore she must have been guilty. And the poor lady was arrested. I think maybe she got off on appeal, or maybe she served time. I don't know. You can read about it here. But she was ultimately let out because people pointed out the flaws in the statistical and probabilistic reasoning that was used at the trial. Lawyers came along and started making these pronouncements about the probability of this is this and the probability of this is this, so therefore we can combine them. And they came up with this figure of 1 in 73 million, but it was based on purely incorrect assumptions. And the judge wasn't an engineer, so he didn't understand, and he just accepted it as true. And the poor lady was arrested and found guilty. And ultimately was freed. But you can read about this. There's a TED, I don't know if you look at the TED Talks, TED, TED Conference. There's a guy who does a very interesting talk about it, and Ben Goldacre in The Guardian writes about it too. So have a read about it. I only mention it because I think it's very important that engineers in particular understand statistics. Because people out there don't understand statistics. And you guys are our best hope. Because the guys up in business school, they don't understand. They're going to use it and try and sell you stuff, okay? And you're our only hope. You guys are engineers. You understand mathematics. You can actually stand up and say, no, this is what happens. Okay, that's my little rant over. Okay, a few more slides, I'll let you go. More random text. Okay, 4 more slides. NUIM, hope you're okay over there. You're very good. I've got 12 people over there still logged in. Fair play to you. Don't laugh. Now I'd like to move on to the assessment. Okay, so again, this is an overview of the assessment. I will be putting up a PDF, a 4 or 5 page PDF with instructions for your assessment. It'll be going up on the website later on today if I can log in remotely from home. Otherwise, I'll have to do it tomorrow from my office. Let's talk about the assessment. The assessment is 4 sections. Here's the first section you're going to have to do. First thing, before I forget, everybody get into a team of 2 or 3 people, preferably 3 people, okay? And send me an email by the end of this week with those 3 people and the name of your team. You want to give a name. If you like giving names to your team, give a name, okay? Send me the details. If I do not hear from you by 5 o'clock on Friday, you will be randomly assigned. Okay, whatever randomly means. Random doesn't mean anything anymore. But you'll be randomly assigned someone, and that rarely ends well because you get someone with very poor hygiene, and you're going to have to sit beside these people in a warm lab. So choose who you like to work with for the next 3 to 5 weeks. Tell me who they are, and that's your team. Okay. And if you don't, if you have trouble, if you can't find a team, that's okay. Tell me, I'll put you in a team. But preferably tell me by Friday. So what will you be doing? These groups of 3 people, you will be doing 4 things. The first thing you'll have to do is make me some nice pictures like this, okay? This is called a fractal. It's called a fractal. It's a fractal. Fractal means fractional dimension, okay? And what it is, this is the complex plane. This is the real axis, and this is the imaginary axis here, okay? And what I've done is I've taken a polynomial, z cubed plus 1, polynomial, z cubed plus 1, where z is a complex number, and it has 3 roots. It has a root at -1, because -1 cubed plus 1 equals 0. There's -1 in the middle of this orange, or this red part. It also has a root up here, a complex valued root here. It has a complex valued root here. Okay. Now, how do you make a picture like this? Well, you make a picture like this by using a technique we will be studying in class called the Newton-Raphson method. It's a method for finding roots. Remember we talked about finding roots a while ago? This is a method for finding roots. And what the Newton-Raphson method does is, starts off with a guess. Guess usually is not the root. There may be a complex number here. And by a process of iteration, it improves that guess until it finds a root. So in this case, were you to start with a guess up here, you apply the Newton-Raphson method, it would find this root, which is in the center of this blue area. Okay? And all of these points in this region converge to here. And that's why I've given them all the same color blue. So all this blue area are all the complex numbers that when you apply this algorithm with these numbers as a start, they converge to this point. And as one would think, all the points nearby converge to that root and consequently join. All the points over here, if you start with these points, they converge to this root. So color them all red. Similarly, all the points in this region here, if you start this algorithm with them, they converge to this root. And I've given them all the color green. That's all pretty straightforward. The interesting stuff happens on the boundary. Along the boundary, it's very chaotic. You start at a point here, it converges to this root. Hence, I've covered it green. A point here, the blue region, you can start with this point, it converges here. And what you can find is, if you zoom in and zoom in, you find lots of pockets of details, all little beautiful patterns and colors and of structures where neighboring points converge to different roots. Even though they're physically very close together, one converges over here, one converges over there. And it's a fractal, which means you can zoom in and zoom in and zoom in and zoom in and keep on zooming in, and this picture keeps on repeating itself over and over and over again. It never stops. It's on forever. Okay? You can stick on some Jimi Hendrix music and have a cigarette and look at it. And a darkened room, it's fun. And that's what I want you to do. I need you to make some of these funny. Okay, that's the first thing you got to do. Make one of these. So the instructions. This is an overview of how you do it. The instructions are in the PDF. What you got to do. Okay, this is just to introduce it. The second part of that debate. Having learned how to do that, I want you to do something really clever. And that's up to you. I don't care what it is. So what clever might mean is developing the code to then maybe automatically identify these interesting regions and zoom in. Then zoom in and zoom in, perhaps. That's one interesting thing you might want to do. You might want to make an animation. Make it spin around. Get really trippy with the whole thing. Okay, that's another thing you could do. There's lots of innovations you could make, and that's your job, to come up with some clever thing and do it. And then impress me on how you do it. Okay? Second thing I want you to do for assessment 4 little things to do with random numbers. I want you to make a random number generator. We're going to cover this in class, and again, the details are in the PDF, which will be on the website. This is only an overview. You're going to make a random number generator and use that random number generator to study the probability of different hands appearing in poker. Poker is a game, card game. You get 5 cards. Varying combinations of cards are stronger than other combinations of cards. You guys are not, you're students, not a poker. But various combinations are less likely than others, and therefore are stronger than others. And you've got to work out what's the probability of various hands of poker, a pair, 2 pair, a royal flush, etc., using a random number generator. I also want you to investigate the birthday paradox. The birthday paradox is the quite unlikely or quite counterintuitive result that if you have quite a small number of people in a room, chances are 2 of them have the same birthday. Okay, so everybody here has a birthday, presumably, unless there's something very strange going on. They all have a birthday. Chances are, I'd say about 95% that 2 people in this room share the same birthday. Almost a second. Someone muted me. Is that you, Manuth? Did you mute me? Okay, so there's about 30 people here in this room. The chances are overwhelming that 2 of you share a birthday. Okay, and this is called the birthday paradox, because when you ask people how many people need to be in a room before it becomes overwhelmingly probable that there's 2 who share a birthday, people think, well, there's 365 days, chances about 200 people. There's so many days of the year, you need lots of people for that to happen. Turns out if you have 20 people in a room, the chances are 50-50 that you have a shared birthday. If you have 30, it goes up to about 80%. If you have 35, it hits to about 90%. Okay? This room, it's almost inevitable. So we'll do it next time. We'll go and talk to your people beside you and find out. And so I want you to investigate that using a random number generator. Make some random people, give them random birthdays, and see how many you need. The Monty Hall game. Oh God, how long do we have to talk about this? This was a game, this is a quiz show in the 1950s in America, in the United States. And the lucky winner at the end of the show was faced with 3 doors. Okay? Behind one of the door was a car. Behind the other 2 doors were goats for some reason. I don't know why goats, but I had goats. Okay? The person would choose a door. I choose door number 1, they would say. At which point, to heighten the excitement, the presenter would then open either door number 2 or door number 3, in other words, the other doors. He'd open one of them to reveal a goat. He would then ask the contestant, you have chosen door number 1. There's a goat behind this door. Do you want to change? Okay. And the person could either stick with his original choice or he could change. And there was a huge controversy in the 50s in the mathematics world because intuitively it looks as if there's no information is gained by finding out where the goat is. That you might as well just stay because it's now just 50-50. There's 2 doors left. You've chosen one, 50-50. But in actual fact, the strategy that pays off is always to change. Once he shows you where a goat is, you should always change because you are now at 2/3 likely to win the car if you change. This is really counterintuitive. You can show it using Bayes' theorem. Okay? And I want you to show it. I want you to simulate it with your Monte Carlo, your pseudo-random number generator, to make a little piece of code that simulates this. Okay? To show that the strategy, the preferred strategy is always to change. Again, the details are in your notes. That's an overview of it. It caused a huge controversy in the 1950s because there was a lady called Marilyn Vos-Savant who had an article in a newspaper, and she pointed out that the logical thing to do was always to change because you now had a 2/3 chance of winning as opposed to 1/3 chance of winning. And she explained this in her article. And some very learned male professors of mathematics, there was a letter, a barrage of letters were published saying this lady, God love her, with her poor female brain, doesn't understand mathematics. And this is typical of what happens when we let women study maths. They make these mistakes. And there was a terrible sequence of letters back and forth until these mathematics professors had to kind of step down and realize, well, actually, we were wrong and she was right the whole time. And it was very embarrassing. And so it is very counterintuitive. It's fooled a lot of people. A lot of people indulge in very cliched, sexist stereotypes when you come across it, but it's an interesting problem. So what I want you to do in the assignment is to investigate it and convince yourself of how it works. And finally, in this one, I want you to compute pi. Okay, so I want you to make a random number generator which makes numbers in 2 dimensions between -1 and +1 on the x-axis and the y-axis. And by observing the proportion of these numbers that fall within the unit circle as opposed to those who fall outside the unit circle, you can estimate pi. I'll let you work out the details for that yourself, but you should be able to work out pi to reasonable accuracy. Okay. Finished. 2 more slides. Assignment number 3, first of all, very straightforward. We're going to solve, I mentioned Havoc and the computer games and all that stuff. I want you to write some algorithms to solve this differential equation and to compare them. Compare how well they work. Which one is best, which one is quickest, which one is most accurate. Then I want you to make a little game for me, or a little simulation of a projectile. You take a projectile, you fling it up in the air. Where is it going to land? How far will it go? Where will it come down? Okay. I want you to do it, first of all, assuming it's a vacuum, so out in space. And then I want you to do it assuming it's not a vacuum and that there's air resistance. Okay. And you'll see that to change the air resistance. So projectile. And then the third part has to innovate. Once you got that working, go and do something clever, like a game, or you can make a golf game, you can make an alien game, you can make an Angry Birds game, whatever you want to do. Some simple little game or some sort of innovation to do something clever. Okay? Finally, after all that, NUIM, you still there? Still awake? Okay, section 4, the last thing I want to do is a small little thing. We're going to study numerical integration. Here is a function. It is impossible to integrate it analytically, but I would like you to integrate it numerically using the various techniques we're going to study in class. This is an identity. It just so happens that you can show this using very complicated maths, that this equals pi squared of. I want you to solve this numerically, and in doing so, use it to create an estimate. So I'm really hung up on finding estimates of pi. I've got 2 questions that require you to make an estimate of pi for me, okay? So this is the second. By solving this numerically, you can estimate this integral. By estimating this integral, you get an estimate of pi squared over 12, and you can use that to get an estimate of pi. And I'd like you to see how many, some people can do pi to how many millions of decimal points. Can you do it to 10 decimal points? Can you solve this integral sufficiently accurately to get pi correct to 10 decimal points or 15 or whatever you can manage, okay? So finally, having done all that, you will be asked to do a 20-minute presentation. Well, Connor in Maynooth is slightly terrified of what he's just heard. It's okay, Connor. We've got 5 weeks to do all this. It'll be okay. So at the end of all this, you will be required to do a group presentation. In that group presentation, you will be required to describe the work you've done. You'll be required to explain to me how your team operated, who did what, how you cooperated, how you shared out the tasks, etc. And another thing I'd like you to do is to go and do what I've just done here. Seek out examples of what we've covered in class on the web. See, can you find examples of all this stuff being used in the real world? Okay, just 1 or 2 examples just to show you. And I'm going to get you to mark each other. Okay, so do a good presentation and then you've got to give each other marks. You can't all give each other 100%. People have tried that in the past. It doesn't work, okay? Okay, has anybody got any questions after all of that? That was just a whistle-stop tour. That looked kind of intimidating. Every year people look at that and go, that looks kind of hard. It is kind of hard, but you have 5 weeks of time. You have lots of help. Everybody manages to do it every year. You will manage to do it. It'll be fine, okay? And you've got lots of support. I can help you. The demonstrators can help you. We're going to do all this in class. And there's lots more detail on the PDF which will be available. Okay, we'll leave it there, and I shall see you on Friday at 2 p.m. Okay, bye-bye, people in Maynooth. See you later.